Welcome. This is the AP Physics 1 Momentum Test Review Sheet solution. Here I'm going over section 2, which is the practice problem. Here you have the first scenario about the coconut. You could read it. A 2 kilograms coconut falls on top of a tree, which is 30 meters above a person's head. The coconut strikes and comes to a rest on the person's head. Justify your answers literally. So a couple of things that I just want to just start labeling here because it says it here. So the mass is here going to be 2 kilograms. There is a height component here, which is 3 milligrams. The coconut strikes and comes to rest, so the final velocity is going to be 0 because it says comes at rest. Alright, so here it says calculate the magnitude of the momentum of the coconut before just hitting the person's head. Right, so we need momentum, or just look for momentum. So momentum is equal to mass times velocity. We have the mass, which is 2 kilograms. We just need the velocity. So our velocity is our question mark. Just before it hits the person's head. It's not 0, just before. So there's a velocity that comes from. Okay. So here, you could try to use one of your old ones, but this is an object falling. Right? This is an object falling. Okay, and if an object is falling, we use our free fall equations. Alright, and the one I should end up using here is going to be my V final squared is going to be my V initial squared plus 2 times it could be delta x if I'm in the x direction, but here it could be delta y. So I have everything here. So I have enough information here to work through the problem. So we are looking for V final squared. So what is our V initial? V initial is going to become 0 because it's at rest from the start, plus 2a. This is just really it's g, right? This is gravity because this is in the y direction, and this is our height, okay? Because that's what delta y is. All right, so you can now plug it in. So you could just square root this if you would like. So it should be V final is equal to the square root of 2, and G is 10. I'm just going to use 10 here. Oops. And the height here is 30 meters. Okay. Once you do this, you should get a velocity is equal to 24 meters per second. All right. You could grab your calculators and work that out. That should be its correct value. So now that we have the velocity, we can now plug it in. So we can go back here. P is equal to my mass, which is 2 kilograms. Our new velocity, which is our 24 right here. Okay. And altogether, our momentum here gets us 48 kilograms times meter over second. Okay, this is a 48. All right. Now it says to calculate the magnitude and direction of the impulse experienced by the coconut in collision with the person's head. Right? So, here's the person's head. Right? Here's the coconut. Right? So there is a calculate the magnitude and direction of the impulse. So impulse is defined by J, which is equal to force times delta t. You might have seen it as change in momentum. Okay, it's equal to force times delta t. Alright, so here, what are the forces? So there is a force down. This is the coconut on the person's head. And there's a force acting opposite to it, which is the force of the head on the coconut. Alright, so the fact that the force, the momentum here is coming down at 48, right? There's an equal momentum at 48 here in the opposite direction. Okay. A person's head experienced a force that is 1,000 newtons in its collision. How long was the coconut in contact with the person's head? Wow, so here it says the F is equal to 110,000 newtons. Okay, and we know that its momentum was really 48. Okay, so they ask what is the time? So T is a question mark. All right, so what we would like to do here is we can do change in momentum is equal to force times delta T. Right, I have a time here, I have a force here, and I have a P here. This is really P final minus P initial. This is force times time final minus time initial. But time initial is 0, so this goes away, and P initial was equal to 0. Okay, so this is what we have. All right, so we have our momentum was 48, our force was 10,000, and this was our time. So divide by 10,000, divide this by 10,000. In the calculator, what does that get me? 1, 2, 3. Get you roughly 0.0048 seconds, which is much less than 1/10. Okay? So it's a very short amount of time for that person to experience that much force. D. A different situation, explain how it would be possible for an identical coconut. Identical coconut is referred to that right here. The M is going to be the same, which is 2 kilograms. That's what they mean by identical. Drop from the same height, but now produces a less force. You want a production of a less force. So if you look at the equation, we have the impulse, which is delta P, is equal to the force times delta T. This time you want a small force. Okay? If you want a small force, if you want this to be small, okay? If you want this to go down, okay? If this goes down, this has to go up. So delta P is still equal to 48. The force can decrease if delta T increase. So increase time. That is how you can produce a 10,000 normal force less. If the time is increased, so that means that the coconut stays hitting on that person's head longer. Okay. 2. Here, a car on the freeway collides with a mosquito, which is initially at rest. Okay, and what happens? Okay, so let me just draw the scenario here. Here's a car. The mass here is very large, very large. Here's a little mosquito, which is a little m. Okay, and okay, and the mosquito here, the velocity here is 0, and the velocity here is going really fast, like 60 miles per hour, which is really fast. Right? So and they hit. Okay, did the total momentum of the car mosquito system, right? I draw the whole thing, and this is the whole system, decrease, increase, or remain the same after the collision. All right, so here we would see that the momentum is conservative. The reason why the momentum is conservative is that the object, okay, because there's no forces that are exerted here except those by the object in the system. So there's no heat, there is no nuclear stuff, It is only the momentum here is conservative because there's no other external forces in this situation. Okay, so here the only forces are the car on the mosquito. So you have the car hitting the mosquito. Okay, so there is a momentum here, and then there's the mosquitoes going to be hit back. Okay, they're basically going to collide. That means that the total momentum of the car mosquito system remains the same. So the total momentum, okay, is remains the same. Okay, we're going to do some calculations down here. So did the momentum of the mosquito increase or decrease? Okay, so before we move on to that, this does not mean 0 equals to 0. It doesn't mean. So this means that if the total momentum coming in was like 100 kilograms per meter squared, so if this was the initial, then the final would also be 100 kilograms times meters seconds. Okay, that's what it means here, that the total remains the same. Okay, here, did the momentum of the mosquito increase or decrease? Okay, the mosquito, right, its change in momentum was defined by mv final minus mv initial. Okay, now we could solve for this. All right, its final velocity was the velocity of the car, and it's initially at rest. So this is like some number minus this is 0 because it was at rest. So delta P is going to be some value here, right? The reason why it is some value, okay, is because the mosquito gains a velocity from the collision by the car. Okay. So here I'm just gonna give it some number. Delta P can just be a very small number, maybe like 0.1 kilogram per meter. Did the momentum of the car increase, decrease, or remain the same after the collision? Here, the car has to lose some momentum. Okay, what I mean by that is that the initial, right, the total here before the scenario was 100 kilograms per meter squared, right? Meters. Then it equals, now the mosquito has a value here, right? It has 0.1. Okay, I'm just making up some numbers. Because this went up originally, do you see how it was 0? Because it went up here to 0.1 kilograms per meter second squared. This had a decrease, so it becomes 9.9 kilograms per meter squared. So the momentum, the car has to lose some momentum because the mosquito gain some. Remember, because the net initial is still 100, so the final is still also 100. 100 what? Kilograms per meter second. Kilograms per meter second. That's what it means. What changed its speed by more in the collision, the car or the mosquito? Okay, so what changed its speed more in the collision, the car or the mosquito? Right? So the car, the mosquito V initial was 0. Its V final was a very large number. The car's initial velocity, let's say, was 60 miles per hour, right? Its final velocity was probably 5.999999999 goes on forever miles per hour. Okay, it loses some because it has to be gained, but the mass of the car is so big. Okay, so what changes its speed more? Is it the car or the mosquito? It would be the mosquito. Why? Because the mass of mosquito was less. Okay, that's the reason why here. Okay, the momentum still had to be conservative, so the velocity had to change, right? Part E. What changed its momentum by more in the collision? The car or the mosquito? All right. So part E, you have to see if the change is more or less. So let's just do this, right? So the car, let's say the car had 100 kilograms per meter squared, okay, and the mosquito was at let's see, 0 kilograms per meter squared, right? This is what its momentum was. This is the initial picture. Okay, here's the final picture. Car, mosquito, right? What changed its momentum more in the collision? All right, so the car, right? The car was going at its momentum had a decrease. Okay, so let's take a look here. So the car had to be lost. The car's momentum lost, right? So this went down. So this went to like a 9.9.9999999. Okay, and this went up from 0 to 0.0001, right? Whatever kilograms per meter second, kilograms times meter squared. What changed its momentum more in this situation? Or did they change by the same amount? So you would say they changed by the same amount. Okay? Because whatever change here had to be the change here. So whatever was lost here was gain here. Whatever. Nah, that's a bad word. Whatever was transferred, the energy and the momentum was transferred here, it still remains here. It's just transferred. So the total initial is equal to the total final. But the energy and momentum was just transferred between the car to the mosquito. Okay. Part F. What experienced a greatest impulse? The car or the mosquito? Okay. All right. So we know that impulse is defined by the delta P is equal to force times delta time. But impulse is defined by the change in momentum. Okay, because they change by the same amount, we would say that the impulse is also going to remain the same for both. Okay, because they change. Because here for E, the momentum change is the same for both because the total momentum remains unchanged. Any momentum gained by the mosquito must be lost by the car. Therefore, the impulse is the same thing because the momentum change is the same for both. Now let's do G. which experienced a greater net force during the collision, the car or the Mosquito? Again, because impulse is equal to F times delta T. Because they have the same P, and it was the same time, F has to be the same because this is the same. So this is the same. If these two are the same, forces also has to be the same. Okay, that's a way you could think about it. Or you could think about this in terms of Newton's third law. Okay, Newton's third law says that the force of the car on the Mosquito is going to be equal to the force of the Mosquito on car. All right, that's Newton's third law, and that applies. Number 3, a car with this mass, okay, 1,500. So let's draw that. Mass is 1,500 kilograms with a speed v is equal to 20 meters over second. And the initial car, this is going to the right? So this is positive. Okay. And the other car is going left. Oh, is it the same mass? Oh, you don't know its mass. Okay. Here you go. Here's the other car. You don't know its mass, but its velocity is what? 10? Please understand this is a minus because, again, it's going the opposite direction. They collide and they stick together. So they hit. So they hit. Okay. Here they get stuck together. And we know that the V here is 5 meters per second. Because it is 5 meters per second, it is traveling to the right. Okay, because it's positive. Calculate the mass of the car. All right, so we could just set that up. M1 V1 plus M2 V2. This is all initial is equal to M1 plus M2 times velocity final. All right, so here this was calculate the mass of B. Oh yeah, because we have that. So what can we do here? Oh, we're trying to get this. So this has to be, let's see, this has to be here. Let me show you. M1 V1 plus M2 V2 is going to be divided by VF, right? This is going to be equal to M plus M2. M2 is this, right? This is 2 and this is 1. So here you would subtract. So it's M1 V1 plus M2 V2 all over VF parentheses subtract M1 is going to be equal to M2. Okay, so you could plug in the values here. It should be what? M1 is 1,500 times 20 plus, oh wait, hold on, but there's an M2 there. How would you have to do this? Give me a second here. Alright, so this just magically appeared on your screen, but I was doing this off the screen. I didn't record it because I might have screwed up something with the algebra. So I went back here at the original because me doing it like this, it would get ugly because you see how the M2 is trapped here? I couldn't solve it. Okay, so I went back here and you could keep track of the algebra here. Okay, so this is the original equation. So what I did is I distributed the VF in here so I could get two separate terms. After that, I subtracted this term to the other side. That's why from here to here, I just subtracted the M1VF into the other side. Okay, then I brought the mass 2 velocity for that over to the other side. So what I have here is I have the mass 1, its initial velocity minus its final velocity on the left, and on my right hand side I have mass 2 its velocity times its velocity final minus its velocity initial. Okay, then because you see how I took out the greatest common factor, which is the mass. Okay, then I could divide this over to get just the mass of the second one by itself. Okay, that's how I got this. So if you want to look how it looks like, this is let me see, 1,500 times V initial, which is 20, subtract its final with 5, then its final velocity was 5, subtract its initial was what? Minus 10. Okay, because again it was going to the left. So, and this equals to m2. Okay, so, or mass 2. So this is 1,500 times 15 divided by 15. Okay, and that should get you your answer. Let's do that. Here times 15 divided by 15. Wait, hold on. The mass 2 cannot be 1,500. It can't be the same. All right, hold on. Let's just check the work, okay? Yeah, the mass 2 has to be 7,500. Something went wrong here. Let me double check the work again. All right, so my mistake here was I read it wrong. It says move left with a common speed of 5, so it was a minus 5. It was a minus 5m, because here, once you subtract the final velocity, it became a 20 plus 5, and on the bottom here, it's negative 5 minus negative 10, which just becomes the 5 here. Okay, so if you do the math here, the 1,500 times 20, this becomes 25. Okay, then divide that by 5, which is the bottom value. Your mass here should get you, your mass 2 should get you 7,500. Okay, there you go. It was from here. Okay, everything was good. The algebra made sense. That's why. It was just my bad values of labeling the velocity. Okay, that was my mistake. All right, so it says here, part B. What happens here was the collision is not elastic. What does that mean? Explain why not. Elastic. Okay, please understand that elastic. What does elastic mean? That the kinetic energy of all the objects combined is the same before and after. Okay, so it means that the energy initial is be equal to the energy final. But it says that the object is what? Stuck together. The object is stuck together. Okay, if the object sticks together, okay, there is heat loss. There is heat loss. Okay, so E, E final is less than E initial. Okay, if you want to see that, you could do the 1/2 mv squared plus 1/2 mv squared. This is of velocity of A times velocity of B. That is going to be equal to mass of velocity. So this is both of them together, velocity squared. Okay, if you work this out, you're going to see how they're not equal. Okay, the initial energy is not equal to the final energy. Okay, but again, it says that's the reason why it's not elastic, because the object sticks together. Okay, if you want to see the proof, work through this calculation. Describe a specific collision between the two cars with the same identical condition, but which is not elastic, in which the car bounce off each other. Oh, that's fairly easy. So it's the same scenario, but this time I'm just going to draw dots, okay? Here you had the mass, which is equal to 1,500, and its velocity is 20 meters, okay? It hits a car like this, boom, and its mass here was 7,500, and the velocity here is, let's see, -10. Okay, in the final picture, all you had to do is that the red car is gonna go off. Okay, well, let's figure out what's the total momentum here. Okay, so let's do the math. What is the total momentum here? P equals 20 times 1,500, and P is equal to -10. -10 times 7,500. Okay, let me do that math. Hold on. 20 times 1,500. So this is 30,000. -10 times 7,500. Okay, this is 75,000. So the total P is equal to, oh, this is negative. So the total was 40, okay, negative kilograms per meters. Right? So that means this total would also be there. So let's say here the object, this one goes, it gets hit, so it goes back. The mass here is the same. This one is also going to be the same. The mass is also the same. Okay, but its velocities are going to be different. So what could this velocity be? Well, I want to make this negative, so it has to be more this side. So it would be less this side. So let's say this time it's going to the right here at let's say 10. Okay, so this becomes some. So oh, that's easy. The P here becomes 75,000. Okay, but the total here has to be negative 4,000, 40,000. Okay, so this. Okay, I need a way so this is more. So 75,000 plus 40,000. 1, 2, 3. So this, the P here, so the P here has to be equal to 1,150,000 because remember the total has to be this. Okay, yeah. So this has to be a minus. Okay, right? Because if we do negative 115,000 add 75,000, you get still the total of negative 5,000. So what is the velocity here? We could do some algebra here by just dividing that times -1, divide that by 15,000. Okay, so the velocity here would be, let's say, negative 7.66 repeating. Okay, so there you go. All right, because again, the total has to be the same. So its momentum here has to combine together to get your negative 40,000 because that was your initial momentum as well. Right? I gave this some arbitrary velocity. So this had to be had in other velocity. Okay? There you go. D. In the collision, elastic part B remain at rest after the collision. Part B. Is the collision elastic when car B remains at rest? Well, it can be at rest after the collision. You can. It's just the energy is being. The other one would just have a velocity change. So yeah, it still can. This can still work. This just becomes 0. Okay, but if you want to see that, I can show it to you if you want. So the total again, your total momentum is negative 40,000. And but the second mass is at rest, so the P here is going to be 0, right? So the net P here is going to be negative 40,000, and that is only produced by this car. Sorry, I should color code it for you. So the first car is red, right? And we know that its total momentum has to be negative 40,000 because the second car, the blue car, the second mass, its momentum is 0. Why? Because it says it right here, car at rest, because its velocity final was 0. Okay, so here, if you did the calculation, P is equal to mv. Okay, this is 40,000. negative 40,000, and its mass was 1,500 times v. So its v has to be equal to what? So we just divide it. So negative 40,000, 1, 2, 3 divided by 1,500. So its velocity here would be negative 26.66. Okay, this would be how it works as well. So the first car just goes back really, really, really fast because the second car is stationary. Okay, how's that possible? It's like the car's like a brick wall, probably. That's why it's stationary. Okay, so it goes back super, super quick. Okay, with a quick velocity. Okay, and it's still elastic. Okay, and that's it. Those are all your solutions.